Welcome to Norton Chemistry. Today we're going to be revising the entire Module 3 in under 1 hour. Get your periodic table ready, as you'll need it as we go through the video. Elements are arranged in order of increasing atomic number in the periodic table. Elements are in periods, which are the rows in the periodic table, and groups, which are the columns of the table. Elements in the same group have similar physical and chemical properties, because they have the same number of outer shell electrons. And the definition of periodicity is the regular repeating patterns of atomic, physical and chemical properties with increasing atomic number. And we can split up the periodic table into the S, P, D and F blocks, which are based on the orbital which the highest energy electron is located in. So I've coloured in each block of the periodic table. So to the left you have the S block. Elements in the S block have the outer shell electrons in the S subshell. You've got the D block in the middle. In the D block elements, the outer shell electrons are located in the D subshell. You've got the P block on the right and the F block at the bottom. Ionization energy measures the energy required to remove electrons from atoms, forming positive ions. So the first ionization energy definition, and this is one you need to remember, is the energy required to remove one electron from each atom in 1 mole of the gaseous element to form 1 mole of gaseous 1+ ions. So for example, the first ionization energy of aluminium we represent using this equation. 1 mole of gaseous aluminium forms 1 mole of gaseous aluminium 1+ ions, and an electron is removed. So we've got a question. Write the equation for the first ionization energy of oxygen. Include state symbols. Never forget to use state symbols when you're writing the equations for ionization energy. So for oxygen, we're going to have a gaseous atom of oxygen going to oxygen 1+ gaseous and losing an electron. Successive ionization energies apply to the removal of electrons after the first ionization energy. So for example, the second ionization energy is when Al1+ goes to Al2+ and you lose an electron. Then the third ionization energy is when Al2+ goes to Al3+ and you form another electron, and so on and so forth. So the trends in successive ionization energies provide evidence for electron shells, so provide evidence for the number of shells and the number of electrons each holds. Within each shell, successive ionization energies increase slightly, as the outer shell is pulled slightly closer to the nucleus as electrons are removed. Between shells, there are larger increases, also known as jumps, in ionization energies, as the electron is removed from a lower energy shell, which is much closer to the nucleus. So for example, we have the first, second, third and fourth ionization energies of aluminium. And you can see that from the first to the second, we have a relatively small jump. From the second to the third, we have another relatively small jump. And then from the third to the fourth, we have a very large jump, a very large increase, as the electrons begin to be removed from the lower energy shell. And you can see this represented in a diagram. So in the aluminium atom, we have 3 shells, and as these 3 electrons are removed from this outer shell, we then start to remove from the second energy level. So once we've removed 3 electrons, then for the fourth ionization energy, we have to remove another electron to remove 4 electrons, and that requires a much larger energy than before because the electrons are so much closer to the nucleus, so there's a much greater nuclear attraction to the electrons. So there are certain factors affecting ionization energies, and I like to remember them using the mnemonic SCAR, but you also need to add an A at the end so it becomes SCARA, but that essentially stands for shielding, charge, atomic radius and attraction. So shielding, or electron shielding, depends on the number of shells. So the lower the number of shells, the lower the electron shielding. Less shielding means greater nuclear attraction. And then we have charge, or nuclear charge. So the greater the number of protons in the nucleus, remember protons are positive, the greater the nuclear charge. Greater charge means greater nuclear attraction to the electrons in the outer shell. Then we have atomic radius. So the greater the number of shells and the smaller the nuclear charge, the greater the atomic radius is. So a smaller radius leads to a greater nuclear attraction because the outer shell electrons are closer to the nucleus. So attraction, the greater the nuclear attraction, the more energy is required to remove an outer shell electron. Therefore, the ionization energy will be greater. So ionization energy is essentially a measure of the nuclear attraction to the outer shell electrons. So periodic trends, shielding remains the same across periods and increases down groups as new energy levels are added. So across a period, there's no new energy levels added, there's no new shells, so the shielding remains the same. Nuclear charge increases across periods as new protons are added to the nucleus, and it increases down groups. However, this increase is outweighed by the increase in atomic radius as new shells are added. And then we have atomic radius, which decreases across periods because the outer shell is pulled closer as the nuclear charge increases. So as protons are added to the nuclear attraction to the outer shell increases, and the nucleus can then pull the outer shell in closer, and therefore the outer electrons become closer to the nucleus. And then it increases down groups as new energy levels are added. And then we have some periodic trends in ionization energies as well. So across periods, the ionization energy actually increases because shielding stays the same, the nuclear charge increases, and the atomic radius decreases. So the nuclear attraction to the outer electrons increases. And then down groups, ionization energies decrease because shielding and atomic radius increases. So that outweighs the increase in nuclear charge. So the nuclear attraction to the outer shell electrons decreases. Here we've got a graph that represents the periodic trends in ionization energies. As we go across the period from hydrogen to helium, the ionization energy increases. Then as we go down a group to lithium from helium, the ionization energy decreases rapidly as a new energy level is added, and therefore shielding and atomic radius increases, which decreases the nuclear attraction to the outer shell electrons very quickly. Then across the period we can see that from lithium to neon, the ionization energy increases again, but from helium to neon, it's not very well represented on the graph, but we should see a decrease in the ionization energy because we're going down the group, and we know that down groups ionization energies decrease. Now you can see that I've circled the anomalies, so we'll talk about those in a bit, but essentially there are some small anomalies in the trend of ionization energies increasing across periods, which is to do with electron configurations, so I'll explain that in a second. So the anomalies are from group 2 to group 3, so for example from beryllium to boron, ionization energy actually decreases slightly as the electrons begin to be removed from the p subshell rather than the s subshell. So the p subshell is higher energy than the s subshell, so the outer electrons are actually further from the nucleus, leading to less nuclear attraction. So less energy is required to remove those electrons. And you can see I've represented that diagrammatically at the top right hand corner. Beryllium has 2 electrons in the 2s subshell and has no electrons in the p subshell. And boron has 2 electrons in the 2s subshell and 1 electron in the 2p subshell. And the 2p subshell is higher energy, so it's further from the nucleus. So there's less nuclear attraction, which leads to this slight anomaly, but then the trend increases afterwards. And then there's also a slight anomaly from group 5 to group 6, so for example nitrogen to oxygen. And the ionization energy decreases slightly because the electrons begin to pair in the p subshell. So paired electrons actually repel each other. So if you remember back to electron configurations, the definition of an orbital is an area of an atom that holds up to 2 electrons of opposite spin. So those electrons spin in opposite directions because electrons are both negatively charged, so they repel each other, and this decreases the energy required to remove the outer electron. And we need to remember that orbitals fill singly first, then they pair. So each orbital in the 2p subshell fills singly and there's no pairing of electrons, whereas in oxygen, you can see in the diagram, we have pairing of electrons in the orbital in the 2p subshell, and that pairing makes it easier for the atom to lose electrons and form a positive ion. Then we have some periodic trends in bonding and structure. So across period 2 and period 3, the trending melting point relates to the bonding and structure. The melting point increases from group 1 to group 4 because the elements have giant structures, so metallic first and then covalent. The melting points decrease from group 4 to 5 because the structure goes from giant to simple molecular, which is only held together by weak intermolecular forces, which require much less energy to overcome than covalent bonds. So you can see that represented on this graph. So you've got the giant structures. So in group 1, 2, 3 and 4, there's a trend of increasing melting points as we go from metallic bonding to covalent bonding. And then from carbon to nitrogen, the melting point rapidly decreases as we go to a simple molecular structure because intermolecular forces, and especially London forces, require much less energy to overcome than strong covalent bonds. So we've got some exam questions. Feel free to have a go and then I'll explain the answer. The trend in the first and second ionization energies of group 2 elements can be linked to the increase in chemical reactivity down the group. The first and second ionization energies of calcium and strontium are given in the table. So we can see that they both have a similar first ionization energy, and the second ionization energy of calcium is slightly larger than the second ionization energy of strontium.